It's interesting, actually, that that particular action happened when it did, because it's really very much relevant to what we're going to be talking about today, which is every time something happens in the industry that is truly disruptive, it creates both opportunities for new players and it creates pain for existing ones. And as a result, a lot of churn tends to happen in an industry that's going through a disruptive innovation. We actually saw this happen in compute over the last couple decades, as I'll explain shortly. And what I'm going to argue today is that the same thing is beginning to happen in storage right now, and it's going to have very profound implications for our industry. And I swear, I wrote these slides before the event happened. Everyone here seen The Matrix? Okay. So I love this quote from Neo at the end, and I think this pretty much describes how it feels when you have something that has been a dominant product and then something comes along like the open source software movement. And I know, by the way, from having been on the receiving end, right? Because having had the lovely high margins of Spark for a long time and then suddenly x86 comes along and just gnaws away at that, well, you know, the higher margins were actually nicer. I liked the bubble. I could do a whole game show. Who used to be a millionaire? You know, it would be a blast. So the general purpose storage revolution, let's first remember what happened in computing over the last couple of years, or really the last couple of decades. If you think back, there used to be, we really had something like a mass extinction event, right? There was like a KT boundary in somewhere around 1990 where roughly a whole bunch of very diverse species just kind of collapsed, and what you were left with was a small core of general purpose computing technologies. If you think about symbolics, for example, it's a fascinating platform. I actually used it when I was in grad school, admittedly mostly to play Flight Simulator, but it was a machine that, the symbolics machines were actually Lisp machines, if you recall. And they would actually, the instruction set was specifically designed to run Lisp programs. It wasn't designed to run any other kind of thing. It wasn't designed to run Fortran. It was specific for Lisp and optimized for that. And at the time, the economics of making such a system were actually compelling. You could get better performance running Lisp programs on one of their systems than you could on a general purpose CPU. I actually spent some time working at MassPar doing the systolic matrix multiply algorithm for it, which was, that really hurts your head. And that, of course, is the Thinking Machines cube over in the corner there. And what happened over time is that those little PCs, they just kept getting faster and more capable over time, and eventually it wasn't economical to make systems like that. The important thing about it is that the thing that ultimately drives this change is not any particular technology. It's not like the x86 instruction set is God's gift to programmers. It's more that something's going to win. Something's going to emerge from that miasma of things. And once it starts to get volume, volume begets volume, and ultimately it's the economic fundamentals that then drive something becoming truly mainstream. And because it's driven by economic fundamentals, as I say, resistance is futile. And I have to say, too, as much as I love Star Trek, in the real world, you know how that scene ends, right? It doesn't end with, you know, Captain Janeway victoriously smashing the Borg. What actually happens is the Borg just crushes the Enterprise. That's the real world. Resistance actually is futile in certain cases. So I believe that this is now happening in storage, and it's happening actually on 3 different fronts. It isn't just about the microprocessor. At the hardware level, it's a question of special purpose hardware like custom RAID cards, custom ASICs, versus volume microprocessors. It's gotten to the point where the amount of work that you could do, just as a for instance, a single Opteron core, suppose you want to generate RAID parity. A single Opteron core can do that at 6 gigabytes a second. You have a hard time finding a RAID card that can go that fast, and Opterons are not that expensive. On the software front, it's a question of special purpose kernels, homegrown things, versus volume operating systems, whether it be Solaris or Linux or Windows or Mac OS. If you have a volume operating system, you have millions of users over whom you amortize your cost of development. Whereas if you're making special purpose kernels for a particular storage device, you only basically can amortize that across as many units as you sell. That means you have to charge a lot more for it. Of course, why do those special purpose kernels come into existence. It's because there was a point in time when using a general purpose operating system wouldn't possibly fit in the hardware available. It consumed too much CPU. Well, first of all, it needed a CPU, and you couldn't afford one of those. And even if you could, it used much more memory than you wanted to have in a device like that. So the economics were not favorable in the past. They are favorable now, especially because of the cost of just doing the software maintenance. And on the networking front, it's special purpose interconnects, whether it be fiber channel or InfiniBand versus Ethernet. So I think that general purpose storage ultimately is going to be inevitable. This is going to happen. People will make very cost-effective systems, very high-performance systems, very reliable systems out of cheap commodity components, and it's going to roughly take a zero off the price that people pay for storage today, just as it did to computing a decade or two ago. The question for us as an industry is, as these devices are created, what will they look like? And what can we do with them? What are the opportunities that get presented by this fundamental change? To see where we're headed, you have to keep in mind that basically to build any kind of storage technology, there's a certain set of parts on the shelf that you have to choose from. And one of them is what your CPU looks like. And if you look at clock rate and core or thread trends on CPUs, a pretty interesting thing happened, which is that Moore's law states that every 18 months you get a doubling in the number of transistors. What happened, though, oddly enough, is that during the last roughly 20 years, Moore's law turned out to apply not only to the number of transistors, but also to the clock rate. Now, Moore's law never said anything about clock rate. It just happened to work out that way. And in fact, if you look at that first bit of the curve from 82 to 02, and that's a log scale, so it's actually super exponential growth, right? That would be a flat line if it were merely exponential. And then in 2002, when we were at about 3 gigahertz, it just kind of hit a wall. And if you look at the roadmaps from any of the major chip vendors, that's not going to change. Right? Nobody's looking at, we're going to have 20 gigahertz CPUs. It's all about how are we going to do something else other than clock rate to get performance up. And there's two reasons for that, actually. One is the speed of light. There's a certain limit that you're put on, that you have put upon you by the fact that 1 gigahertz corresponds to 1 nanosecond, which is 1 light foot. That's a really, really short distance. So once you start talking about a 10 gigahertz part, now you're talking about you've got this much distance for signal if it were going at light speed, and it's actually only going at electron speed, and it's going through a not especially friendly material. So you have that working against you, and you have another factor, which is that the power consumption goes up super linearly with clock rate. And one of the big focuses that people have now is on how do we get the power consumption down in data centers. There's a trend line or a threshold that was crossed within the last couple of years where IT spending, people have figured out now, they spend more on running the equipment than they do on purchase. And so power in particular is something that is driving the desire to not just have everything constantly getting faster, but more focus on what can I do at a lower clock rate? What can I do with a slower RPM drive? But meanwhile, as the clock rate has sort of stalled, the number of cores or threads that you're getting per CPU is on an exponential tear now. So AMD is already at 4 cores, Intel's already at 4, Sun's already at 8, and in fact there's 64 threads there because there's 8 threads per core, which means that what you really have in effect is a Starfire class machine in every socket. So as much as we've been focused as an industry on horizontal scale over the last, say, 5 years in particular, now vertical scale is actually poised to make a comeback because it's not a question of some giant refrigerator-sized computer that has tens of boards in it. It's some little tiny thing, a single chip that you can hold in your hand is going to have tens of cores in the very near future, or actually in the very near present. So